Okay, so hi everyone. I manage the Catchment Assessment team in the Midlands and Eastern Region of LAWPRO. Our Catchment Scientists, they work in areas for action. In the second cycle, we had 190 of these, expanding out to about 340 or so in the third cycle. Within these catchments, we use integrated catchment management techniques to refine the understanding of water quality impacts within those rivers or lakes or groundwater, and we make significant pressure referrals then to implementing bodies to inspire action. In relation to agriculture, one of our key roles within the catchment assessment team is to provide local, understandable and relatable scientific water quality information to farmers on the ground. And that information is relayed through the advisor service provided by the ASAP programme. Our assessment is quite detailed. We start with a desk study assessment. Following on from that, we have community information meetings with both the wider community and the agricultural sector. We do detailed data analysis on the various receptors within the catchment. We make significant pressure referrals, and then we engage in the communication process with the implementing bodies on those referrals. So it's a lengthy process. But when we looked at the landscape this year, particularly I suppose maybe the changing attitude and maybe the increased understanding of nitrates as a national issue, we felt there was a need to tailor our process and to streamline our approach to nitrogen so that we could get as much information out and targeted advice out in 2024 as possible to allow the bulk of the year to be spent implementing measures and giving targeted advice rather than waiting for us to do the more detailed assessment. So we really tried to look at our approach and see whether we could justify doing that. So we've been out on site now, out in catchments for a number of years, and we have learned a bit about nitrogen and particularly how to characterise it. So there are some considerations to think about when assessing the impact of nitrogen on rivers, for example. The biological assessments that it's one of our key tools in our toolkit, I suppose, to assess the impact on rivers. It's less useful to narrow down on diffuse nitrate issues. It's very useful from a point source perspective, where if we go upstream and downstream of a point source, we'll see that reflected in the biology and we can infer that it's significant. Similarly for phosphate, where you have phosphate coming in at dedicated pinch points along the stream, we can oftentimes see a change in the biology upstream and downstream of one of those flow pathways. But because nitrogen is a truly diffuse issue, and because those pathways are coming in under the ground, uniformly along the kind of perpendicular to a stream, for example, we don't really see the reaction in the biology, so it's less useful to us. In a similar vein, the stream walks are also less useful to characterise nitrogen pathways. To contrast it with the phosphorus example, we can go out during rainfall events, we can track the pathways moving over land carrying phosphorus and sediment into rivers, we can put a measure or an interception measure in place to block that, but for nitrogen it's coming in under the ground, so we can't really use our stream walks to as good an effect to characterise or refine the significance of nitrate. So we rely on chemistry and loading analysis, and typically tributary scale is sufficient for that analysis. The interannual concentrations of nitrogen, they're less erratic than phosphorus, and you see disproportionately large N loads occurring during the recharge period, which is typically October to March each year, and I'll touch on that on subsequent slides and how we designed our approach to N. And finally then, look, we're talking a lot about measures today, but resolving diffuse nitrate losses, it really is an area's game. The more hectares of high pip N or high risk land for diffuse N losses that have measures introduced or bespoke advice given on timing, the more the nitrogen load to groundwater streams and estuaries can be reduced. So prior to embarking on our kind of strategic nitrates assessment in early 2024, we needed to put our third cycle priority areas for action into an estuarine context. So we created nitrogen load apportionment models for all of the major estuaries requiring N load reductions. This would have built upon what the EPA produced in 2021, where they would have looked at all of the major estuaries and kind of gave a total load discharging to each estuary along with a total load reduction target for each of those estuaries. But the catchments are huge. For example, the Barrow estuary has over 140 river water bodies within it, kind of intersecting with 5 different counties. So we decided to localise that analysis to see how our PAAs fitted into that over the next number of years. And off the back of that, we looked at N load reduction targets set for each estuary, but also the relative contribution of all of the main rivers within those larger estuarine catchments. And from our perspective, how much each of our priority areas for action, how many tonnes of nitrogen was each contributing, and how can we assess that? So this is an excerpt from one of those models for the Barrow. I don't expect you to be able to read what's on this. There's a lot of data on it. But going from right to left, the rightmost column here is the nitrogen load for each of the water bodies within the barrow. Now, this is only a section of it. The load was calculated by multiplying a 3-year average N concentration by the average flow in the stream. So it's real data, it's not a model load as such. And it's tracked then from upstream to downstream, from the headwaters of the barrow the whole way down till it meets the estuary out near New Ross. And it tracks then on a water body scale. You can kind of see it on the top left graph here, even though you probably can't see the values. You can see how the nitrogen in the main channel kind of evolves over time. But then you can also see below that which systems are contributing the highest tonnage of nitrogen as they come into that main channel. And we use that then to prioritize our work in this particular assessment for our areas for action. So based upon the models that we had created, we decided which areas for action we would, I suppose, prioritize nearly as pilots to see if this approach would work in early 2024 and see if we could get a significant amount of referrals done in a time that was a lot less than it typically takes us to get referrals done. So we prioritised 12 priority areas for action for a Q1 2024 assessment, which included the Grease PAA in the Barrow Estuarine Catchment, the Blackwater Kells, Lower Kinnegad and Upper Boyne in the Boyne Catchment, the Ban, Doreen and Black Lion in the Slaney Catchment, and then 5 PAAs within the Blackwater Catchment in the southwest. Across those 12 priority areas for action, we assessed 81 water bodies, covering 3 different regions: the Midlands and Eastern Region, which is mine, well, not actually mine, but I manage it. God, it's all coming out now. The Southeastern Region and the Southwestern Region. Across those 81 water bodies, we assessed 350 locations, and at those locations, we collected chemistry. We looked at flow information so we could calculate nutrient loads, but we also took the opportunity to assess the hydromorphology of each of those sites. You know, we're assessing nitrogen here from the perspective that it is an estuarine issue, for sure. You know, most estuaries are N-limited, but it's not the only issue in these areas. So we took the opportunity to assess the habitat in all of them. Let's take a quick drink of water. So that kind of covers the, I suppose, the where and the why, and to a degree the how. But the when assessing nitrogen is equally as important, and particularly when you're collecting limited data, you have to really try your best to collect a representative sample. So this is an example of a monitoring point, which is give or take about 5 kilometres upstream of the Barrow, Upper Barrow estuary near New Ross. It plots total oxidized nitrogen from 2011 to 2023. The amber dots here are the annual average each year. The kind of the blue crosses there are the spot samples at this particular site. There's chemistry collected on a monthly basis. And then the red line there going across your screen is the transitional water body threshold of 2.6. In a way, that's the kind of target that we're trying to reach in the stream in the main channel before it discharges to the estuary. From our perspective, while your eye might immediately get drawn to, well, how has it varied over the last 10 years and what does that mean? From our perspective, and that is important, but from our perspective, we were interested in each year, how is the nitrogen concentration varying in these catchments, and can we decide when to do our assessment to match the time of worst impact? And you do see kind of a uniformity, if it's even just simply plotting all of the sample occasions when the transitional water threshold of 2.6 was doubled. So that's what that dashed line at the top is there. It's double the 2.6 threshold. And you can see that invariably our highest concentrations occurred during what I call the recharge period. So January, February and March were the months where we typically saw the highest concentrations of nitrogen in the Barrow River before it discharged to the estuary. Concentrations are only one part of the story, and probably a more important driver is the load being lost to the estuary. So if we were to take the annual average concentration in 2023 in the Barrow River before it discharges to the estuary and multiply that by the flow in the river over the course of the year, it equates to about 5,000 tonnes of nitrogen being lost to the estuary per year. But that 5,000 tonnes is not lost uniformly throughout a calendar year. You know, it's lost during kind of particular events. So you can see the pattern that I outlined of kind of higher concentrations during the more winter months, that it's very much exacerbated when you look, or even the pattern is higher even when you look at the load in the stream over the course of a given year. So what I've added in here is nitrogen load in tonnes per day corresponding to those water chemistry samples. And what you see is really disproportionately high loads being lost during the winter period, up to 60 tonnes per day, versus comparatively smaller loads happening during the summer period, down below 10 tonnes per day. So it was really important that when we did this assessment, we were hitting those periods to collect the samples. So just when we looked at the Barrow estuary, we saw this pattern, but then when we looked at all of the other estuaries, we saw a remarkable consistency in that pattern of load losses in the main channels discharging to the estuaries. So just to flesh out why conceptually that is happening, I've just taken a few bits of information and put them onto the one graph to explain. So shown by the green line here is the 2023 grass growth, that's a national grass growth curve that was provided to me by Teagasc. I've added to this the kind of yellow bars on the x-axis, that's the soil moisture deficit, and then on top there coming down is the effective rainfall. Now, while the soil moisture deficit it can sound like an intimidating term, it's actually very simple. You can conceptualize the soil out in the catchment as a dry sponge. Whenever you pour water onto that, water doesn't come out the bottom of that sponge straight away, but once all the pores in that sponge are full of water, any more water you put on equals leaching, and that's what the soil moisture deficit is. So when you have a soil moisture deficit, you don't have leaching to groundwater, you don't have N losses. The effective rainfall, that's equal to the total rainfall minus evapotranspiration minus the soil moisture deficit. So essentially what these bars on top are telling you is telling you that leaching is happening, and it's telling you the volume of leaching that's happening. So if you then compare that with what we're seeing in the streams, that in January, February, March, we're seeing very high load losses of nitrogen. If you focus in kind of from the October onward period, your grass growth are steadily declining. Your recharge period is officially in gear, seen from all the rain coming down. You have no soil moisture deficit. So if you take that as the kind of start at that point, nitrate is starting to move. And the nitrate in the soil is what's accumulated throughout the year, so any nitrogen that was in excess of the grass growth requirement. Once it starts to move, it starts to percolate downwards through the soil and subsoil. Once it gets to the water table, it's transported horizontally into the stream and off to the estuary. So from a measures perspective, if we take the start of October as when our nitrogen has started to move, and it turning up in our streams in large loads in January, February, March, we can see that in a lot of Irish catchments, the time lag is low. That's a positive thing, because it means if we reduce the surplus of nitrogen in our soil in October, we should see a net improvement the following kind of winter, spring, less of a load loss. So it's good from a measures perspective. So it was very important that LAWPRO targeted this period when the largest loads were being lost, and we did. The square here shows when we carried out the assessment, we were in what's called Q15 flows, which means you've got very high stream flow, which means all those kind of delivery pathways are active, transporting that surplus into the stream. And when we collected our chemistry samples, we were capturing that. So I'll spend the last couple of minutes just focusing in on one of those catchments and what we found. So as I mentioned, we've replicated this in 12 different PAAs across 81 water bodies within the LAWPRO work plan, or are currently trying to replicate it. So this is the Grease Priority Area for Action. It's a tributary of the main Barrow River, just kind of east of Athy. It discharges then into the Barrow River, and the estuary itself is about 90 kilometres downstream of that. The catchment is made up of both pasture and tillage, about 70% pasture and 30% tillage, and there are 10 Water Framework Directive water bodies within it. And within those 10 water bodies, there are 16 WFD monitoring points, so a couple of different types of monitoring points there. So as with the main channel graph, the amber dots here represent the annual average. You have your threshold lines, and you can see your spot samples given by the kind of the blue crosses. So without focusing in on the temporal trend, there are some key points that we can pick out of this from a mitigation perspective. The baseline nitrogen concentration from 2021 to 2023 was 5.67 milligrams of N per litre. If we set and that equates to 517 tonnes of nitrogen being lost to the Barrow estuary per year. If you remember, the total load being lost to the estuary was around about 5,000 tonnes, so the Grease River itself is contributing about 10% of the load to the estuary, so we know that actions we take here will have a net positive impact on the estuarine status. That 500 tonnes of nitrogen equates to a per hectare load of about 38 kg N per hectare per year, and that will become more relevant in subsequent slides. So if we then set ourselves a target that we want to reach 2.6 at the base of the Grease River, if that's the concentration threshold we want to reach with our mitigation, It means taking out about 280 tonnes of nitrogen from the catchment, stopping that from getting to the groundwater, which then goes to the river, which then goes to the estuary. And that equates to 20 kilograms of N per hectare per year. So in essence, that's the target we need to reach with both our compliance and our mitigation or supplementary measures. If we reach that, we can say with relative assurance that we'll get to approximately 2.6 in the river. So that gives context to everything that we're doing. Sorry, let's go back one slide there. Yeah. So at the start of our assessment of the Grease River, we had 10 WFD water bodies, but we broke the PAA down into 26 topographical subcatchments. And each of these subcatchments had either one or multiple monitoring points within them, and we sampled those monitoring points during those high flow events. I've also shown here the groundwater vulnerability map. This is a combination of subsoil permeability and thickness, and it's more vulnerable if you have a low subsoil permeability and a higher clay content. So that you can see that throughout the Grease catchment, most of the catchment is either high to extreme, so there's a high hydrological susceptibility for nitrate losses in this catchment. Looking at that in plan view, you can see the black outlines here are our 26 topographical subcatchments, and we have our variety of monitoring points then, 34 in total, where we sampled nitrogen and loads. The nitrogen concentration in those high flows that we measured were 2.9 to 6.6, so everything was above the 2.6 threshold, so we can say that there are diffuse losses throughout the catchment, but there were certainly areas within the catchment where we had much higher concentrations. The concentrations are one thing, but as I mentioned, one of the roles of LAWPRO is to provide understandable and relatable information to farmers through the ASAP programme. Concentrations don't mean a huge amount to farmers, but giving loads does. So using the concentration and the flows within each of those subcatchments, we were able to work out how many kilograms of nitrogen per hectare per year were being lost from each of those subcatchments. So we remember that on average across the whole catchment, we were losing about 38 kilograms of N per hectare per year. We've arranged throughout the subcatchments from about 2.4 to 70. So there are areas that are losing higher amounts of nitrogen proportionally, but we're also giving these figures through the ASAP programme to the farmer. You have this load in each subcatchment, and that can then be directly compared with what the surplus being lost from that farm is. And one of the measures through EIP is to quantify those surpluses. So each referral has an N concentration profile from the nearest WFD monitoring point, the contribution to the estuary, the N load per hectare per year, and also any additional information that we collected during the high flow events. So finally then, my last 2 slides, I'm nearly there. It's all well and good for LAWPRO to provide specific scientific information that's understandable and relatable to be given to the farmers and to give a steer on where the highest areas of impact are within the catchment. But then the next step needs to be detailed engagement by the ASAP programme, and then the question of resources comes into it. In diffuse nitrogen catchments, there tends to be an awful lot of farms for the ASAP programme to visit. In other catchments, if we identify a point source, for example, and that's a significant impact, it could be one farm visit to identify it, to resolve it. Whereas in diffuse nitrate catchments, the farm numbers tend to be very high, so we have to look at an approach to refine that. So shown on the right here is the pollution impact potential for N that you're all very used to seeing, with rank 1 being highest potential impact and 7 being the lowest. And in the Grease catchment, we have 377 farms. So that's a lot of visits to do in a catchment that's impacted throughout. The total amount of farms that have the highest risk land for N on them, so PIP rank 1 to 3, is 340. And if we subtract out all the farms that have less than 1 hectare of the highest risk land, that gets you down to 237. That's still too high a number from an ASAP resources perspective. A very productive advisor might get to 80 farms per year, and that's a really significant number when you factor in revisits. So if I refer on a catchment with 237, I'm giving basically 4 years of work to an advisor, and the resource simply isn't there to do that. So we looked at a method to kind of try and prioritise within the pollution impact potential maps. And essentially what we did as part of our nitrates assessment was to characterise how many hectares of PIP rank 1 to 3, which is the highest risk land for nitrogen loss, every single farm in the catchment has, and then rank them according to kind of categories. And what we came out with was 4 categories in the Grease catchment. So Grease category 1, there are 12 farms, and together those 12 farms make up 24% of all of the high risk, the highest PIP land within the catchment. Category 2, you have 35 farms, and each farm within that category has between 30 and 50 hectares of high PIP, together making up 33%. Category 3 is 20 to 50 hectares of high PIP, 65 farms making up 28%. and category 4 is the remainder. So each farm has between 1 and 20 hectares of high PIP, 125 farms making up 14% of all the high-risk land in the catchment for N losses. So this is not saying that you only focus on the farms which have the highest amount of high PIP, but the farms which do have the highest amount of high PIP, a visit to those farms is a bigger bang for buck than going for a farm that has a small proportion of it. If you went to every one of those grease category 4 farms, it'd be 125 visits, about a year and a half of work for an advisor, but you'd only be hitting 14% of the nitrogen load. So it's important to give context to what we do in these catchments, and then to join that context up with the low production targets that we have and actually track progress. So finally, we collected data sets during the high flow conditions for 12 priority areas for action, assessing 351 sites. We always hear about the right measure and the right place, but I suppose from a local catchment perspective, it's the local catchment assessment in the right place at the right time. Context is very important, as are tangible water quality targets. When you say you have 5,000 tonnes leaving the Barrow River going into the estuary, and to achieve good status, you need to half that and take 2,000 out or 2,500 out. It's such a large target over such a large area, it's very difficult then to relay that to the farmer on the ground, so you need to make the information local. So I suppose our role is to build in the existing data sets to refine the understanding. Everything that I presented today in terms of the data analysis that we've done is publicly available data, with the exception of the samples that we collected in the field, so there's lots of data out there to work with. We prioritise where measures will be most effective, but nearly the most important thing is to provide that local, understandable water quality information to advisors and farmers at a scale and in a format that is relatable to both. In doing so, you're facilitating change. Before finishing, I'd just like to say thank you to you as the audience, but also thanks to my team, the Catchment Scientists in the Midlands and Eastern Region, and to all the other catchment assessment teams throughout the LAWPRO organisations that helped out in doing all of this work. Thanks very much.